All right, so equilibria of solutions in solutions of acids, weak acids and bases. A lot of fun stuff here now. So reminding ourselves about the equilibrium expression. Here is an acid. It's dissociated into H3O plus and A minus. We don't include the water in the equilibrium expression, so the equilibrium expression looks like this. Concentration of products over concentrations of reactions. Do you remember this stuff?
Yeah, I remember. That's the equilibrium expression.
If we have a Ka, and now you've noticed, I don't know if you've noticed, but sometimes they put a little letter down here to kind of talk about the K of, what kind of K you are referring to, like Kw in last chapter. That was just referring to water's dissociation. It's always the same anyways. It's the product of the products raised to their reactants over the product of the concentration, or the product of the concentration of the reactants raised to their coefficients. All right? So don't get confused by Ka, Kw, Kp, or whatever. All right? Just always remember that that is an equilibrium expression. Therefore, it's always the mass action expression. Products over reactants. All right. Well, these Ks for acids, which we call Kas, they are very well known, tabulated. We have them in our chapter 16, 16.1 in our book here. And we can also have what are called the pKas, which is the negative log of Kas. And we'll talk more about that. Now, again, we want to emphasize here that when we take the p function of something, it's just taking the negative log of it, all right? And again, it's just a function to allow us to kind of converse about numbers that change logarithmically, all right? So don't get too excited about what this means, because it could be pH, pOH, as we've seen, pKw, pKa. There's lots of different things you can do with this negative log function, which we will use. So, all right. Bases behave like this. A base takes a proton from an acid, sometimes water. This is the auto dissociation, or not the auto dissociation, but the dissociation that occurs in water, right? The Kb then, the K for this reaction, is where you have the concentration of products over the concentration of the base. Water, again, is not included. Do you remember why?
Oh, because it's a liquid. You don't include liquid or solids in the mass action expressions.
That's right. Very good. pKb is the negative log of your Kb. And again, we have a table of the Kb's for lots of different bases. So which of the following is the product in the acid ionization of H2CO3? Which of the following is a product?
H2CO3 will dissociate into HCO3 minus and a water molecule, or a hydrogen ion.
Very good. That's right. So HCO3 is the product of the dissociation. This would be the product of the dissociation of HCO3 minus, right? And water is where the hydrogen ion goes for H2CO3, if you want to include the water, right? Okay. Now remember this chart?
Kind of do, yeah.
So what is it showing us?
That if you have a really strong acid, then its base, its conjugate base, is not a very good base, not a very strong base. But if you have a very weak acid, its conjugate base is a very strong base.
Okay, that's right. Very good. And what we see is that for these conjugate pairs, there's a relationship between the Ka of the acid and the Kb of its conjugate base. And it is that Ka times Kb equals Kw. All right? And that also means that pKa pKa plus pKb equals pKw. Do you remember, got to make sure these are all big Ks. Do you remember what pKw is?
Let's see, POH plus pH equal pKw. So pKw must be 14.
That's right, it's 14. pKw is, now let's go back just for review. Kw is the H2O dissociates into H plus and OH minus. Kw, the K, the dissociation constant for this dissociation is the hydrogen ion concentration, that product, times the other one, hydroxide ion concentration. And we said that it always equals 1 times 10 to the minus 14. The concentrations of these then are 1 times 10 to the minus 7. The negative log of 1 times 10 to the minus 7 equals 7. So that's why pH of water all by itself is always 7. The pOH is also 7, equals the pH there. The pOH equals 7. pOH plus pH plus pH equals pKw, all right? pKa plus pKb also equals pKw, all right? Which, again, to get Kw equals Ka times Kb, you take the negative log of them, and then the sum of those, instead of the product here, equals the negative log of the Kw. Okay, so pKa plus pKb will equal 14. Now that is for conjugate acid-base pairs, right? So if I have the, let's see here, here is an acid, acetic acid. Its Ka value is 1 times 10 to the minus 8. No, sorry, 1.8 times 10 to the minus 5. Get a fresh piece of paper here. Ka for acetic acid is 1.8 times 10 to the minus 5. Therefore, its pKa is, what is this pKa? If its Ka is 1.8 times 10 to the minus 5, what's the pKa?
pKa, is that just the negative log?
That's right. pKa is negative log. So I go negative log of 1.8 times 10 to the minus 5. 4.74. Okay? That means that the pKb for the acetate ion, its conjugate base pair, is 14 minus that value there. Whoops. 14 minus that value, 9.26. This is the pKb for the acetate ion. This is the pKa for acetic acid. Again, pKa plus pKb for its conjugate base equals pKw. Also, Ka times Kb of the conjugate base equals Kw. So Ka 1.8 times 10 to the minus 5 times Kb equals 1 times 10 to the minus 14. So 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. 5.56 times 10 to the minus 10. That is the Kb of the conjugate base, the acetate ion here. And again, I should be able to get that by taking the negative log of or not negative log, going from the pKb to the Kb, 10 to the minus 9.26. That should equal, again, my 5.5 times 10 to the minus 10. Okay? Great. Important relationships. pKa plus pKb equals pKw. Ka times Kb equals Kw. pOH plus pH equals pKw, which is 14. All right? Lots of important relationships to realize there. So what's the Kb for sodium fluoride? Well, we need to know that the Ka for HF is 6.8 times 10 to the minus 4. We need to get that. If we didn't have that, we could look it up online, but you could always look up what's the Kb for the fluoride ion, right? But the Ka for HF is 6.8 times 10 to the minus 4. So Kw, 1 times 10 to the minus 14, divided by this will give us our Kb for what? What would that be the Kb for?
Well, Ka is for hydrofluoric acid, so Kb then must be for its conjugate base, which is F minus.
That's right. Very good. So 1.5 times 10 to the minus 11. Again, that's 1 times 10 to the minus 14 divided by 6.8 times 10 to the minus 4. How about this one? If hydrocyanic acid is 6.2 times 10 to the minus 10, what is the pKb, or sorry, the Kb for the cyanide ion?
I'll try it in my calculator.
Okay, everybody at home, you try it in your calculator. Make sure you can get your scientific notation to work out okay.
So it's 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 10.
Forgot to put the divided by sign. (1.6 times 10 to the minus 5).
Okay.
How about the Ka for this compound if I know that the Kb for ammonium, or the ammonia ion, is 1.8 times 10 to the minus 5?
Same thing. 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. That should give us the Ka for the ammonium ion.
Very good. This one here, we have a Kb of 4.1 times 10 to the minus 10.
Then 1 times 10 to the minus 14 divided by 4.1 times 10 to the minus 10. That's it.
Excellent. All right. Very good. Ka for benzoic acid. What's the Kb for sodium benzoate?
Oh, it's just 1.0 times 10 to the minus 14 divided by 6.28 times 10 to the minus 5. So it's probably going to be C.
I think you got lucky. You didn't do it, did you?
No, I didn't, but I can see it's not going to be B. You're not going to get the same number. It's going to be different, but it's going to have 10 to the minus 10.
Okay, very good. All right. So now we come to a point where we have the ability to determine the pH of aqueous weak acid solutions. And this is a lot of fun. What we do is we use our ice tables. We use our ice tables and we use the pKa's or the Ka's of our acids, and we identify to what degree the dissociation will occur, and from that we can identify the pH from the resulting hydrogen ion concentration. All right, and now remember that we can drop that X term. Do you remember dropping that X term?
Well, a while ago.